We've been using the power rule for a couple of weeks now to take the derivative of lots of kinds of functions. But you might have noticed that we only actually proved the power rule when this exponent is a whole number, a positive whole number. What about when n is a negative number? Can we prove it then? Okay, let's start easy. Let's take the derivative of x to the -1 without using the power rule, because that's what we're trying to show is valid. So this derivative will be the same thing as the derivative of x to the -1 is the same function as 1 over x. So I could actually use the quotient rule on this problem since I haven't actually, since I'm not using the power rule, I can use the quotient rule. So by the quotient rule, the derivative of this function would be, well, the lower function times the derivative of the upper function is 1, so its derivative is 0, minus the upper function times the derivative of the lower function, well, the derivative of x is just 1, divided by the lower function squared. Right, so that didn't have anything to do with power rule, just the quotient rule. And so now I simplify, x times 0 is 0, and 1 times 1 is 1, so I have -1 over x squared, which I could rewrite as -1 times x to the -2 power. So in fact, we got the derivative of x to the -1 is -1 times x to the -1 minus 1. We could even write that. 1 times x to the -1 minus 1. And so the power rule works for just 1 over x. Okay, that's good, but I want to be able to do more exponents than just those, so let's look at a general negative exponent. So I want to take the derivative of 1 over x to the n, or x to the -n, for n to be a positive integer. Well, let's just do exactly the same thing we just did. So this is the same thing as the derivative of 1 over x to the n, and I know now that since n is a positive integer, I know that I've already proved the power rule for x to the n when n is positive, so I can use that in this case. Again, by the quotient rule, what do I have? Well, I have the lower function, x to the n, times the derivative of the top function, well, that's 0, minus the bottom function, no, the top function, make sure you get it right, times the derivative of the bottom function. And again, since n is a positive integer, we've already proved the power rule in that case, so I can say n times x to the n minus 1. Right? And so then I divide everything by x to the n squared. All right, so let's clean this up and see what we get. X to the n times 0 is just 0, and so what I have here in the top is minus n times x to the n minus 1, and in the bottom x to the n squared, that would be x to the 2n. So this is minus n times x to the n minus 1 times x to the, well, 2n in the denominator is minus 2n, like this. And so simplifying still, minus n, x to the n minus 1 times x to the minus 2n, I add those exponents together. So I have n minus 1 minus 2n. So this is minus n x to the, well, n minus 2n is minus n. So this is minus n minus 1. And look at that. Again, we have the power rule. So now, as long as n is an integer, I can say that I know the power rule holds for x to the n. Whether it's a positive integer or a negative integer, I now have my proof. Okay, so the power rule is true for any integer values of n. But what about fractional values? What if I have irrational exponents? Let's take a look at that. Here's our next case. We want to talk about rational exponents. So I want to talk about rational exponents in general, but it's a little bit easier to just consider a specific example, x to the 1 over 12. So we'll see that there's actually nothing special about 12, and so then this will look like a specific proof but give us a general proof. I want to use a different one of our tricks here. So I want to take the derivative of x to the 1 over 12. So what I want is dy dx for y equals x to the 1 over 12. Well, okay, so x to the 1 over 12 is pretty hard to understand, so this relationship is the same thing as saying y to the 12th power gives me x, right? So now I can use my implicit differentiation to find my dy dx. So I differentiate this side. This is a positive power, so I already know that the power rule works in that case. So I get, well, 12 times y to the 11th power times, using the chain rule, my dy dx. And differentiating on the other side, the derivative of x is just 1. So now I have to rearrange this. I end up with dy dx is equal to 1 over 12 y to the 11th power. So let's rewrite this as 1 over 12 times 1 over y to the 11th power. Well, I know exactly what y is. It's x to the 1 over 12. So this is 1/12 times 1 over y to the 11th power, and y is x to the 1 over 12 to the 11th power. So using the rules of exponents, this x to the 1 over 12 to the 11th power is, so I have 1 over 12 times 1 over x to the 11 over 12, and 1 over x to the 11 over 12 is 1/12 times x to the negative 11 over 12, which is, in fact, if I take 1 over 12 minus 1, I get negative 11 over 12. So in this case, we get that the power rule holds for this particular exponent. Well, and there's nothing special about 12. If this was 17, then here I would have 17 y to the 16th, 17 y to the 16th, etc., and then I would end up with 16 over 17, negative 16 over 17, and 1 over 17 here. So no matter what positive integer I put in the denominator here, 1 over that integer, I get the result that I want. Well, what if I don't have a 1 in the numerator? By way of example again, let's look at taking the derivative of x to the 15 over 12. Well, this is the same as the derivative of x to the 1 over 12 raised to the 15th power using the rules of exponents. Now this is a positive integer, so I already know that the chain rule works, I already know that the power rule works for this case, and I use the chain rule with this function here because I know now the derivative of x to the 1 over 12. So using the chain rule, I get 15 times the inside function, x to the 1 over 12 to the 14, times the derivative of x to the 1 over 12, which we just found is 1 over 12, x to the negative 11 over 12. So simplifying this, I have the 15 and the 1 over 12, so I can combine that to be 15 over 12. And then I have x to the 1/12 to the 14th, so that's x to the 14 over 12, times x to the negative 11 over 12. So 15 over 12, x to the, well, adding these together, thankfully they have the same denominator, so it's not too bad. I get x to the 3 over 12, which is, in fact, 15 over 12, x to the 15 over 12 minus 1. So again, the power rule works in this case. And again, there's nothing really special about the 15 or the 12, so we have the power rule for all rational exponents. At this point, you might think we're done, but we're not, actually, because there's a whole other class of numbers, the irrational numbers. Maybe you've never actually seen an irrational number in the exponent, but it's definitely something we could do, and we really want the power rule to still work in that case. But the first thing that we have to understand is what actually is an irrational exponent. After we understand that, maybe we can understand a proof. So now I have a function with an irrational exponent, and first I want to understand what that even means. So I understand pretty well what would be happening with the function y equals x to the 1.4, right? This would be the same thing as x to the 14, and then I take the 1 over 10 power, right? And I understand pretty well what would be happening with the function x to the 1.41, right? This would be the same thing as x to the 141 to the 1 over 100 power, right? And so I understand these rational exponents, I understand these integer exponents, so I understand decimal exponents. So still I could say, well, I understand pretty well what's going on with x to the 1.414, or y x to the 1.4142, or y equals x to the 1.41421, and so on and so on and so on, right? And so basically the idea is when I have this number, square root of 2, which is the limit of this sort of process, whatever this is, then I am getting closer and closer and closer to whatever this function is, y equals x to the square root of 2 power. So, okay, it's not too hard to imagine what is actually going on here as long as I understand what's going on with these decimal exponents. So what, in fact, is the derivative of this function? Okay, well, again, so I have y equals x to the square root of 2 power, and that square root of 2 in the exponent is pretty hard to understand, so I want it out. And the best way I know to get something out of the exponent is to take a log. So let's take the log of both sides. So this means that the log of y is equal to the log of x to the square root of 2 power, which means that the log of y is equal to the square root of 2 times the log of x, right? Because this exponent here jumps off the log down to the front. So, all right, now I can take the derivative of both sides of this function. So taking the derivative, the log of y, the derivative is 1 over y times dy dx, using the chain rule. On this side I have this coefficient, square root of 2, and the derivative of log x is just 1 over x. So feeling pretty good, I can multiply both sides by this y, get dy dx is equal to the square root of 2 times y over x. Alright, so then square root of 2 times y over x, well I know what y is, it's x to the square root of 2 power, so this is square root of 2, x to the square root of 2 over x, well, and x to the square root of 2 over x, this is like x to the 1 in the denominator, so I can combine these two exponents by saying this is the square root of 2 times x to the square root of 2 minus 1. Right? Well, and actually, that's exactly what the power rule says that I should be getting. I should take the exponent, it jumps off and goes here, and then the new exponent is whatever I had before, minus 1. And that's exactly what I got in this case. So, and again, this actually doesn't have anything to do with the square root of 2. Any old number that I put there would be fine. And even other kinds of numbers, right? I could have put rational numbers there, I could put integers there. In fact, I could put any n. So if I just replace the square root of 2 everywhere in my proof here by just n, I see an even more general proof that the power rule holds for any n. All right, now we're done. We've actually proved the power rule for any value of n. Any number that you can come up with, unless it's imaginary, of course. We're only dealing with real numbers here. Any number n that you can come up with, the power rule is true. So keep on using it the way that you have been for the last couple of weeks. If you have questions, make sure you post on the forum, and I'll see you all later.